and actually the talk will be a combination of both. So I will try to explain some basic facts about entire curves, I mean holomorphic curves, and their applications to algebraic geometry and possibly to number theory. So let me start with a few definitions, but the pointer is apparently not working. Technical problem? Okay, so minor technical problem. Okay, so it works now. We are considering entire curves. So an entire curve will mean a non-constant holomorphic map from the whole complex line C into a complex n-dimensional manifold X. We are, of course, interested in the existence of such maps. So if you take an open subset in Cn, which is assumed to be bounded, then you can apply Liouville's theorem, and you conclude that there are no such curves because bounded holomorphic maps are constant on the complex line. If you take the Riemann sphere minus the points 0, 1, and infinity, which is the same as C minus 0, 1, then you have no entire curve either because of Picard's theorem. On the other hand, if you take a complex torus, so I mean by this the quotient of Cn by a lattice, then you have a lot of entire curves. Since C is simply connected, you can lift any holomorphic map from C to the torus as a map twiddle F from C to Cn, which is just an n-tuple of holomorphic entire functions on the complex line, and therefore you have uncountably many such curves. Okay, and we are interested actually in algebraic varieties, so we are considering complex projective space, just the quotient of Cn plus 1 minus 0 by C star, and one denotes by Z0 with, I don't remember the English word for this, but so 2 points, Z1 and Zn, and this is the equivalence class of the point Z. And then it's easy to show that an entire curve into projective space is just obtained by putting n plus 1 holomorphic functions which have no common zeros. And there are, of course, a lot of them. Now, more generally, we consider projective manifolds. By this, we mean a subvariety of Pn, which is defined by a collection of polynomials. And for this to make sense, we have to assume that the polynomials are homogeneous. So Pj is homogeneous of some degree dj. And we assume that x is non-singular, which, of course, means that you have a suitable condition on the polynomials Pj's. Okay, now we have a few general concepts for complex manifolds. So one can define so-called Kobayashi pseudometric. So you pick a point x in manifold capital X and a tangent vector xi, and then you define the infinitesimal pseudometric. So it's some kind of element of length, kappa x of xi, is just the infimum on positive numbers lambda, such that there exists a holomorphic map from the unit disk D into X, which sends the origin of the disk to the point small x, which maps the unit tangent vector at the origin of the disk to the vector xi in the manifold with the scalar correction lambda. And let me write a few things. So, of course, for instance, if you have a holomorphic map which is defined on the whole complex line, then, of course, you can restrict to a large disk of radius r, and then you can rescale on the unit disk by defining f restricted to the unit disk of t to be f of rt, and then, of course, the derivative at the origin of this map, f hat, is multiplied by the radius, and therefore you have larger and larger derivatives. Because you have very large derivative, you can therefore take the coefficient lambda to be very small as you like, and therefore you easily conclude from this argument that the Kobayashi metric is identically zero along the vectors which are tangent to the holomorphic curve. Of course, if you are in Cn or Pn, you have such lines everywhere, and therefore the Kobayashi metric on Cn or Pn is identically zero. Or on Cn or Pn, or similarly on tori, you have a lot of entire curves, and the Kobayashi metric is identically zero. So, on the contrary, you define a complex manifold X to be hyperbolic in the sense of Kobayashi if you are not in this situation, but the associated integrated pseudo distance is a distance. So you just pick 2 points, A and B. You take, as usual, an arbitrary differentiable path from A to B, and then you integrate, suppose gamma is defined from 0, 1 into X, you integrate the element of length, which will be, in this case, just the Kobayashi element on the tangent vector, which is the derivative of the curve, and you integrate this, and then you get the Kobayashi length, so it's the length of your path gamma, and then, as usual, for a Riemannian metric, you take the infimum of this for any path joining 2 points, and then you get the distance. So you require this distance to be a real distance, namely that the distance of different points is non-zero. So you require that Kobayashi metric of 2 distinct points is really strictly positive. And then if this is true, you say that X is hyperbolic in the sense of Kobayashi. Something very interesting occurs in the case of compact manifolds. In this case, there is a very well-known theorem of Audi, which tells you that X is Kobayashi hyperbolic if and only if there are no entire curves from C to X. The reason for this is that you have compactness. If you have larger and larger disks, actually you can find a suitable subsequence which will converge after rescaling the disks to a map on the whole disk. So the precise statement is that if you have maps from the unit disk, you have a sequence of maps, G nu, on the unit disk into X, such that somewhere, for instance, at the origin, the derivative goes to infinity, then you can select maybe a small disk somewhere And then you can make a change of parameter, which depends on nu. So you will compose G nu with this change of parameter, phi nu, from the disk into itself, such that this thing actually will converge. Or you should also rescale. Sorry, I forgot. So it's a large radius here. And after you rescale, this converges to f, and f will be an entire curve. So I will not do this. This is an elementary application of Schwarz lemma. And you conclude the statement of Brody's theorem. Hyperbolic varieties are interesting for many reasons. So one of them is potential consequences for number theory. And for instance, there is this well-known conjecture by Serge Lang. So if you have a projective variety defined over Q, and you assume this variety is hyperbolic, then it should be true that the points which are rational points, so which have rational coordinates in projective space, is a finite set. So it gives you a very strong statement about the finiteness of solutions of Diophantine equations. And on the other hand, of course, you see easily that if the variety is not hyperbolic, especially if you have a holomorphic map, which is, say, a rational map. So if there exists a rational map, which therefore will be holomorphic, from the complex line into X, which extends to P1, if this map is defined over Q, so with rational coefficients, if you take the rationals here, this will be contained in the rational points. And therefore, if you have such a map, it's a reason for the existence of infinitely many points. So you expect that somehow this condition, by replacing also rational maps by transcendental ones, so you have coverings of elliptic curves as well, you should consider. So you assume that if you have such a property, then on the other hand, you will have finiteness of solutions of Diophantine equations. And in dimension 1, this is known to be true by Falting's result, a very famous result which was proved in '83. So let me continue with complex curves, so namely complex dimension 1. So in this case, for non-singular curves, situation is very easy. You can classify curves by their genus. So a genus is a number of holes. So genus 0 means you have a sphere, and then the curvature is positive. So in the sense of complex geometry, you are looking at the so-called canonical line bundle, so Kx, which is defined at the bottom of the screen. So the canonical bundle is just the determinant of the cotangent bundle, so lambda n t star x. Its degree is 2 times the genus minus 2, 2g minus 2. So for a sphere, it's negative. So the Ricci curvature is positive, but the canonical is negative. So the signs are opposite. For the torus, you have genus 1, 2g minus 2 is 0. The curvature is identically 0. The torus can be made to be flat. And for genus at least 2, then Kx is strictly positive, and you have negative Ricci curvature. For hyperbolicity, then this has immediate consequences. So for P1 is not hyperbolic, you have a lot of entire curves. Elliptic curves are not hyperbolic. But if you take genus at least 2, then it's well known that the universal cover of a curve like this is the disk. So the curve is just the quotient of the disk by a discrete subgroup acting without fixed points. And by lifting holomorphic maps, you will conclude from Liouville's theorem that you have no such entire curves, and therefore X is hyperbolic. In dimension n, Kobayashi already in the 70s, in the early 70s, showed that if Tx is negatively curved, then X is hyperbolic. This assumption is the assumption, for instance, that the cotangent bundle is ample. So in algebraic geometry, one says that the holomorphic vector bundle is ample if you have a lot of sections in the symmetric powers, Sm of E. More precisely, for a large multiple, M, then the global sections of Sm of E should have global sections which generate all one-jets of germs of sections at any point. So all possible differential at order 1 are generated. And for instance, the quotient of a bounded symmetric domain by a group automorphism is such negatively curved variety. Okay, so now we need another definition. So a non-singular projective variety is said to be of general type if you have the maximal possible growth of the so-called pluricanonical sections. So the pluricanonical sections are, by definition, sections of the tensor multiples of the canonical bundle. So locally, in coordinates, they are of the form some holomorphic function f of z multiplied by a holomorphic form of maximal degree, dz1, wedge, etc., wedge dzn raised to some power m. You assume that the number of these sections grows at maximum rate, so some positive constant times m to the n, where n is the complex dimension. A basic example is when you take a non-singular hypersurface, xn in Pn plus 1 of degree d, then the canonical bundle is the tautological bundle of projective space with the coefficient d minus n minus 2, O of d minus n minus 2. And this is ample if and only if d is at least n plus 2. So for large degree, larger than dimension plus 2, you have a variety of general type. And now there is a property which is strongly expected to be true, but still a conjecture of general type, that if a manifold compact manifold is hyperbolic, then it should be of general type. And therefore, in some sense, the Ricci curvature should be negative, although this means negativity with some poles. So it's not smoothly negative, but would mean negative for some singular metric which provides some poles. I will not check this here. And now we have the following theorem, which is not extremely hard. So you consider a number of properties, so 4 properties. So P1, X is hyperbolic. P2, every subvariety y of x is of general type. P3, it's an effective uniform bound on the algebraic curves in x. So you pick C, a curve in x, which might be singular. So you consider its desingularization C bar, what people call the normalization, and you look at the Euler characteristic of the desingularization. So 2g of C bar minus 2. Actually, it's the opposite of the Euler characteristic. And then this should be strictly positive and uniformly bounded below by a multiple of the degree of the curve. If you have such a bound, you say that x is algebraically hyperbolic. The fourth property, which I will not define immediately, but only slightly later, is some kind of negative curvature property but for some more sophisticated concept of curvature, which is the jet curvature, I will define this later. And then, essentially, we expect that these four properties are equivalent, but unfortunately, we can prove only a number of implications. So, one basic fact is that P4 implies P1. So if you know some kind of negativity of curvature, you can prove hyperbolicity. Essentially, you can prove this by consequences of the Schwarz lemma. So it's just a sophisticated version of the Schwarz lemma, as the Alford-Schwarz lemma, actually. And then you prove from this that P4 implies P1. And also, P4 is very strong, and if you know this, you know essentially everything. So P4 implies everything. Now, P1 implies P3. So maybe I should comment this, because this is easy to somehow to understand why this holds true. So you assume that X is hyperbolic. So this means that you have no map from the complex line into X. And now you assume that you have a sequence of curves which contradicts estimate P3. So suppose you have a sequence, sinew, of curves in X, then you desingularize the curves, and then you can map, of course, the desingularization to the curve, and then you embed in X. And this, of course, in general, will be covered by the unit disk. If it is not covered by the disk, it's because you already have a rational or an elliptic curve. If you are in this situation, then it's not possible because you assume X is hyperbolic. So this should be of genus at least 2. And now this gives you a sequence of holomorphic maps from the disk. Here it's the universal covering. And then it's not hard to show that if you take the ratio which is the Euler minus the Euler characteristic by the degree, then by the Gauss-Bonnet formula, this is essentially the average of the curvature. This is essentially the area of the curve. So this is the integral of the area. But then if this ratio goes to 0, it means that somehow the curvature in average is very small compared to the area, which means that the derivative of the curve actually will be very large, and therefore you will conclude that there exists a point P nu in the disk, which you can assume to be 0 actually, by just a change of variable, such that the derivative will become very large. It's just because you pick the point where the average is the worst. Well, okay. But then by Brody theorem, you can, after renormalization, get an entire, from this, you make the sequence converge to an entire holomorphic map, and then you get the contradiction. Okay, and now if the conjecture on general type holds true, then it should be true that P1 implies P2. Okay, so let me come now to another. So I still have this technical problem. pointer is stopped. Okay, so I'm continuing with the mouse. Okay. No, it's the. Okay, now you have another fundamental conjecture, which is the so-called Green-Griffiths-Lang conjecture. If you take a variety of general type, so for instance, a hypersurface in Pn+1 of large degree, then there should exist a proper algebraic subvariety, y in X, in which all entire curves should sit. So there should be a locus. So if you take X of general type, X of general type, then there should exist some locus, y, here, such that all maps from the complex line sit. I mean, all the curves should be forced to map into one. This is a conjecture, of course. If you assume that these two conjectures are proved, so the conjecture on general type and the conjecture of Green-Griffiths, then actually you would get a purely algebraic characterization of hyperbolicity, namely P1 and P2 should be equivalent. Well, it's an easy fact by induction on dimension, because if you assume dimension is, the conjecture is of course clearly true in dimension 1, well known, and therefore if you assume that every subvariety is of general type, there is no way by induction on dimension that a holomorphic curve non-constant can exist. Okay. Now let me come to the fundamental parts of this talk, so which is a new method which has been developed very recently in the last decade and in the last years to try to prove the main conjectures. So you are writing the curve locally in coordinates as just an n-tuple of holomorphic functions, f1 of t, etc., fn of t. And then the main idea is to use algebraic differential operators. So these operators, contrary to what you are used to, maybe operate on holomorphic curves. So usually the differential operators people are using are operators on functions on X, so into real or complex numbers. But here we don't look at this. We look instead at operators which act on entire curves or germs of curves. They have some order k, so they depend on the first k derivatives, and they are supposed to be algebraic in terms of the derivatives, so they are given by some monomials in terms of the first, second, and k's derivative. And also they depend at each point by holomorphic coordinates. So the coefficients a, alpha 1, alpha 2, alpha k are holomorphic functions on X, and they are taken precisely at the point hit by the curve, which is f of t. So actually the operator depends only on the k-jet of the curve, namely the Taylor expansion of the order k at each point. And then you have a C star action. The C star action is very easy. It's just amounts to rescaling the parameter t by a factor lambda. And then, of course, the k's derivative is multiplied by lambda to the k. And therefore, if you look at this C star action, you have a concept of homogeneity. You have a homogeneous polynomial if p gets multiplied by lambda to the m when you look at this C star action. It just means that you are looking at operators whose total number of derivatives is m. So for instance, if you look at something like Wronskian, so let me write something in dimension 2. So if you look at a Wronskian, something like this, f1 prime, f2 double prime minus f2 prime, f1 double prime. So this is an operator of order 2, k is equal to 2, because you have the maximum order of derivatives is 2, and then the degree, which I denote always by m, is 3. This is the degree. Why is this 3? Because you just count the number of primes. You have 1, 2, 3 primes. Okay, so degree is 3. And of course, you can have arbitrary complicated operators. This type. The collection of all such operators, point by point, can be organized into a vector bundle. The vector bundle is just given by the collection of coefficients a, alpha 1, alpha 2, alpha k. It's a finite dimensional set of parameters. Because of the change of coordinates, you have a vector bundle. We denote this vector bundle by EKM. And the letters GG means Green and Griffith, because there will be a different one later, which is quite similar. And now we come to the fundamental vanishing theorem. So the fundamental vanishing theorem is that if you have a global algebraic differential operator, P, which is everywhere defined and everywhere holomorphic, but you assume that it vanishes, the coefficient vanish on some ample divisor. So you assume that there exists a divisor A on which the coefficients of your operator vanish. And you assume that this divisor is ample. This means that it can be deformed to cover the whole variety and can be turned in all directions. Okay, so it's ample. Or very ample, but it's not very important. Okay, then if you have such a global operator, then automatically all entire curves have to be solutions. So if you happen to find such a global operator, you know a priori that your entire curves have to be solutions of this. And the proof is a bit involved. It uses Nevanlina theory and second main theorem and some non-trivial argument. But there is a very simple case where the proof is almost obvious. Namely, it's the case when you assume that the derivative of the curve is bounded. So assume that your curve has a bounded derivative. So it's of course defined over C, so it's not compact. But you assume that for some Hermitian metric on X, here this will be bounded by some constant. This case is very significant because actually when you have a curve such that the derivative grows, you can always extract by Brody lemma a limiting curve in the cluster set which will have bounded derivative. It's because of the renormalization statement which I gave. So actually, if you can exclude bounded curves with bounded derivative, you exclude all holomorphic curves. So it's somehow it's the crucial case. Okay, but in this case, of course, you can apply Cauchy's inequalities. It's well known by the Cauchy formula that if you have a bound on a holomorphic function, you can bound the higher derivatives divided by the radius of the disk where you are. But here you can take disks of fixed radius 1, say, and therefore all derivatives are bounded. With respect to some Hermitian metric on the manifold, which is compact. But therefore, now, when you apply your differential operator, you get also something bounded. But then you can apply Liouville's theorem, and therefore this has to be constant. But then you can move the ample divisor to hit the curve, and then this constant function will have to vanish somewhere, and therefore it is identically 0. So it's a very easy proof. Okay, and now we come to geometric construction. So actually you take the quotient of the germs of k-jets of curves by the C star action. It's easy to see that you get a fiber bundle, which is holomorphic. It is equipped with some universal line bundle. I will not prove that here, but the differential operators are just the direct image sheaf of the tautological line bundle. So we try again the pointer, so it works again. Okay, thank you very much. Okay. Now, if you use this idea, so you have a bundle. So xk is just the jets of the curves divided by C star, essentially. The regular curves, non-constant curves. Okay, so there are the jets here. So saying that your curve satisfies some differential equation, is the same as saying that it's lifting. So you have a case lifting here, which is just the k-jet. So at any point t in the complex line, you associate the k-jet. And then saying this just means that the case lifting here will have its image sitting in some divisor zk in x, and this divisor is precisely defined by the polynomial p, because you have one condition here which links the derivatives, and one condition on these derivatives define a codimension 1 subvariety zk in x, and you are just saying this. Okay, so finding a differential equation just means finding an algebraic relation in terms of the derivatives. It's quite obvious, but it's needed. And now what you expect is that you will find a lot of different equations. So you expect to find not just one equation P, but a lot of them, P1, P capital N. And then you will have corresponding divisors here, Z1k, Z2k, Zkn. And then you take the intersection of these, And you expect that the intersection of those divisors will project down. So you have this intersection upstairs, and you expect that this intersection will project to something which is a proper subvariety here. So you expect somehow to have enough differential equations to constrain the curve downstairs into an algebraic subvariety. However, somehow, well, this was the attempt by Green and Griffiths, was at the end of the 70s. But there is one fact that they didn't observe at that time, namely that there are a lot of differential equations which are completely useless. By this, I mean, for instance, if you look at an equation like this, f2 double prime is 0, this is a completely useless equation. Because f2 double prime is 0 just means that f2 is an affine function in some coordinates. But then, of course, your curve can be reparametrized by any automorphism of C, for instance, or of well, any entire map from C to C, and then, of course, you lose the fact that this is an affine function. And therefore, the fact that this is an affine function is completely irrelevant. And therefore, this equation has absolutely no meaning. On the other hand, if you have a Wronskian, so f1 prime, f2 double prime minus f2 prime, f1 double prime, such an equation is very meaningful because having the Wronskian to vanish means that your curve sits in a line in these coordinates. Being a solution of a Wronskian means that the two components f1 and f2 are dependent. So this is meaningful. Of course, you can look at higher Wronskians, f prime wedge f double prime wedge fk, and then a solution of this means that the curve will sit in some linear subspace in the given coordinates. And it turns out that you can define a concept of invariant differential operators by this relation here, which I will write in general. So an invariant operator is an operator P which acts on curves such that after you reparameterize, of course, the reparameterization here will create some derivatives, but you assume that only the first one will appear with some exponent here. Of course, if you would take the second derivative, it's not at all the case, because if you take the second derivative of a composition of f2 with phi, you certainly get double derivatives of phi as well. But for Wronskian, things just cancel, and you get only the first derivative. So you assume that you have operators like this. So, for instance, all combinations of Wronskians are okay. But what it can show that there are also other operators which do not depend only on Wronskians. And then you get a new bundle, which is a subbundle of EGG, which is the bundle of interesting operators. So these are all operators. These are the invariant ones. somehow the invariant operators are operators which describe the geometric locus of the curve, independently of the parametrization. And now you can put this into a framework, which is a more abstract framework, but is very suitable to calculations. Namely, you introduce a category, the category of directed manifolds. So what are the objects? They are just pairs. So you take a projective variety, and then at each point, you select some holomorphic, some complex subspace of the tangent space, and you assume that this subspace varies holomorphically. You don't assume any integrability. Therefore, you have a distribution, but it's not necessarily integrable. And then the arrows are just holomorphic maps. Denoted by C here. So there will be maps from X to Y, which map also the differential maps V into the given distribution of subspaces W here. So this makes a category. The absolute case is the case where you have no constraint, and no constraint means that V is just the full tangent space, so you don't require anything on the tangents. And you have also the relative case. The relative case is when you have a map from X to some parameter space, and then you look at the relative tangent space, and then you require, for instance, that your maps will sit in the fibers. So this is another interesting case. And the integrable case is when the distribution V will satisfy Frobenius conditions, and then you will get foliation, holomorphic foliation, non-singular, but you might also take V to be a sheaf, and then it might have singularities. And then there is a functor. The functor is the functor one-jet. So again, it's very easy. So suppose you have such a distribution of subspaces, and then suppose you have a curve which is tangent to this distribution. Okay, so you have a curve which is tangent to V. The markers are drawing out, so I'm not sure you see them very well. So here you are on XV. But now you are interested only in the tangents. So you look at the derivative, and of course this makes a point in the projectivized bundle. So instead of looking at V, you look at the projective space of V. And then, of course, this is a new variety. Which somehow incorporates the points and the tangents. It turned out that on this variety, you have a very natural bundle, which is the set of tangent vectors. So I denote them by C. And of course, you have a projection pi to X, and you assume that they project down to precisely the tautological line here. So if you pick a point X V here, it means that you have a point which is a line in the projective space. You take tangent vectors which project into that line. And in this way, you define a new sub-bundle in the tangent bundle of X, twiddle. This is the functor. And now the basic fact is that if you lift a curve, so you have a curve F, you can associate its first jet. So its first jet is just the curve itself and its derivative. And now it's very easy to show that if the curve F is tangent to V, then its first jet is tangent to V twiddle. And then, of course, you can iterate. Therefore, you will get a K-jet. You will get some directed pair, XK, VK. I call this a projectivized K-jet. So you look not just at the jet as usual, but you take only directions. And then, well, I will skip this. You have a number of basic exact sequences which describe the geometry of these objects. Well, it's a bit technical, so I will skip that. And of course, you get a tower because you can iterate. So you have the K-jets, and then if you forget the K's derivative, you go into the K-1 jets, etc. The fibers here, this is a projectivized bundle of some distribution of subspaces Vk-1. So it's a tower into two projective spaces. The geometry is very intricate, but very interesting. Well, I will skip this. And then it turns out that you have, because of this, you have a tautological line bundle here. And then it turns out that you can show that the global sections of the multiple, so if you raise this to some multiple, so you denote this by OXK of M. And then if you look at the global holomorphic sections of this on the K-jet space, what you get is precisely the invariant differential operator. So this is canonically isomorphic to the bundle EKM, which I defined restricted for the curves that are tangent to V. Okay. Using this technology, then, in the last 15 years, we've been able to solve a number of conjectures. The first theorem which was solved was a solution of the Kobayashi conjecture. So the Kobayashi conjecture is that if you have a hypersurface in Pn of large degree, which is generic, so you pick the coefficients at random, then it should be hyperbolic. Hyperbolicity should be a generic property for large degree. This is of course very clear for curves, but was unknown for surfaces. Then it was proved in 1988 by myself and one of my students, Jawer El-Ghoul, that if you have degree at least 21, then a generic surface in P3 is of degree at least 21 is hyperbolic. And McQuillan independently, but we use also his techniques, proved it for degree 35. In 2004, this was improved by Mihai Paun, which got to degree 18. And Paun uses other techniques which I will describe in 1 or 2 minutes. Sophisticated techniques which come from the work of Claire Voisin. And very recently, three authors, so Erwan Rousseau, Joël Mercœur, and Simone Di Verio. So Simone is one of my latest PhD students. So combining their results on the course of a few years, they just proved the Green-Griffiths conjecture for hypersurfaces in Pn+1. So of course this is still far away from solving the conjecture for arbitrary algebraic varieties, but it's already a very big step, because somehow any projective algebraic variety is at least bimeromorphic to a hypersurface of high degree, of some degree in projective space. So this is already quite substantial. So I will explain a little bit more about that. Okay, one basic thing which we need is to understand the algebraic structure of the ring of differential operators. It might look surprising, but we don't even know if the ring of the invariant differential operators is finitely generated. We can try computations. So if you look at order 1, so only one derivative, so it's very easy. The operators depend on f1 prime, f2 prime, fn prime, and any choice works. So you get a polynomial ring, obviously. For order 2, it can be shown that the operators depend only on the Wronskians. So again, it's finitely generated by the first derivatives and by the partial Wronskians. For order 3, it's still known to be true, but it doesn't depend only on the Wronskians, but on some kind of derivatives of the Wronskians of higher order, which are written on the blackboard here. So it's a ring A32 in dimension 2. So it's not a polynomial ring, but an extension of degree 2 of a polynomial ring. In order 4 and 5, we still understand. So the conjecture of finiteness of generation is proved in that case. For order 4, it's a non-Galois degree 6 extension of some polynomial ring with some very strange generators. In dimension 5, it has been computed with a computer after many hours, many failed attempts, and shutting down Rome because the main computer in Rome was so overloaded by the calculation that it stopped everything. But anyway, it finally succeeded. So we found 2,935 generators or something like that. So it was done by Joël Mercœur. So it works. For order 6 and more, we don't know. Then the strategy is to compute Euler characteristics. So because we know the geometry of the bundle, we know the Chern classes, so we can compute the Euler characteristic. And the Euler characteristic gives the alternate sum of dimensions of cohomology, so H0 minus H1 plus H2, etc. It turns out that for surfaces, you can show easily that H2 vanishes. So you know H0 minus H1, you calculate. Because H1 is positive, you have a lower bound on H0. And now a lower bound on H0 is very good because it tells you that you have a lot of operators. So it gives you a lower bound on the number of operators. This is the way that El Ghul and myself proved the conjecture in '98. The trouble in higher dimensions is that you don't know about the intermediate cohomology groups. It has been shown by Erwan Rousseau that they don't vanish. So it makes the situation quite hard. But the main conjecture still is that you have the generalized Green-Griffiths. So it's the same as Green-Griffiths, but for curves which are tangent to a distribution of subspaces V. And you replace, in that case, condition that X is of general type by the fact that V is of general type, which means that the determinant of V star should be a big line bundle. So it has positive curvature. And then you have the same conclusion for curves which are tangent to V. So I will not explain the strategy because I'm running out of time. But essentially, you are using induction on dimension and on order. So you have a double induction. You make an induction on the order of the differential equations and an induction on the dimension of the base variety. And then you replace the Riemann-Rohr calculation by some more elementary estimate, which is a version of Morse inequalities for the complex cohomology. This is called the holomorphic Morse inequalities. So this is something I first introduced in very long ago, in '85. But in this situation, it's only a very, very simple special case, which tells you that if you have some numerical intersection condition, which is written down, a to the n minus n, a to the n minus 1 times b, positive, then the difference O of a minus b as a line bundle has a lot of sections. And then very recently, Simone Di Verio used this thing by applying this to the geometry of the jet spaces, made computations, and could prove for general hypersurfaces in projective space that you do have these operators. So this is the way it was done. This proves at least one equation, but you need more, as I explained earlier. So you need several equations. And then you use another technique which was introduced by Yung-Chong Hsu in the early years of the millennium, so 2000, or 2001, etc. So you are using global holomorphic or meromorphic vector fields. So having one polynomial is not enough, but the point is that you can differentiate them by using holomorphic vector fields, and then you get new polynomials that can still be used. This depends on understanding the meromorphic vector fields on the jet spaces. This was carried out by Joël Mercœur, making very, very delicate calculations in the last 2 years. This is how the Green-Griffiths conjecture was solved, essentially. So I will not give any technical detail about that, but it's roughly the main idea. So I will stop here.